Okay, so welcome everyone to another TCS Plus talk. Today we have Rahul Ilango, who's a PhD student at MIT, and he'll be telling us about the minimum circuit size problem. Okay,
Great.
Rahul, let me spotlight.
Thanks for that introduction. And I want to start by thanking the organizers for setting this all up and being very accommodating. So I'll be talking a little bit about whether it's NP hard to distinguish order from chaos. And this is going to be based on a result that showed that the multi-output circuit minimization problem is NP hard. And that was joint work with Bruno at the University of Porto and Igor at the University of Warwick. So before I begin my talk, I just want to say a little bit about like what the goal is here. Obviously, TCS Plus has like a very broad audience, and I just want to say what like the aim in my talk is going to be. And I think for the general TCS audience, I just want to get across that there's like some problem called MCSP, and it's pretty cool. Historically, aesthetically, theoretically, it has like some very interesting properties. And then maybe there's some people who are, interested in thinking about this problem and working it in kind of the subfield. And I just want to kind of give what my personal perspective on the problem is and like maybe some open questions in the area. And then finally, I guess there are going to be some MCSP experts. As you can see, Einstein studied slight variant of MCSP. And for them, I want to give them like some taste of what this multi-output result is and like how it's proved. And so I think based on like what the audience is, I'm going to kind of focus more in on these first 2 points. That's going to be my main focus, and I kind of want to paint the picture of what the story of MCSP is so far. What do we know about the problem? Why is it interesting? And where is it going to go next? So I'm going to give some taste of how this result is proved. And I just want to say there's actually a talk given by my co-author, Bruno, who gave a really great talk that's available on YouTube, which goes into much more detail than I am going to go into this result. So if you're interested in seeing more about that, I'd highly recommend going to see that. All right, so what is MCSP, or the minimum circuit size problem? And so kind of the context that MCSP comes from is asking what is the complexity of a string. So like you have 2 strings here. This string is like very ordered. First half of the string is 0s, second half of the string is 1s, and like here's a string I got from like random.org. It doesn't seem to have any specific pattern, but like so it's kind of intuitive to us to say, okay, this string has low complexity. This string seems to have like not very much order, but like how can we formalize that? And there was this idea that a bunch of people came up with in the 60s. It's like that you can kind of formalize this by asking how hard is it to compute this string? Like you can formalize this quantity of like complexity using computation. And specifically in a setting we're going to be looking at, you can like look at this function which says, if I want to produce the ith bit of this string, what is that bit? So like f sub w is going to be like, you get to input in binary what bit you want, and then it's going to output, what that bit is. And then you can ask like, how complex is this function? And for us, like the way we're going to measure the complexity of a string is going to be like, what is the size of the smallest circuit computing this function? What is the size of the smallest circuit that outputs the ith bit of the string w? And so formally, MCSP is going to be this problem which has as input some string you want to know the complexity about, some integer s, and output, is there a circuit computing this function of size less than s? And so I'm going to go over the definition of MCSP a little bit like more formally again. And I'll say more about what I mean by circuit and stuff like that there. But like just at the beginning of the talk, I wanted to kind of say what this problem is. And there's a couple different perspectives you could have on this problem. So the one is the perspective I just said, where you want to know what the complexity of a string is. Another very natural interpretation is like to view MCSP as this problem of like local compression, where you have some string W and like, it's a very long string, and in practice you only want to know at a given time like what's the ith bit of the string. You might say, and instead of storing like the huge long string, you want to store some smaller object like a circuit that will let you say what the ith bit is, but be much more efficient about that. So you can think of MCSP as like a local compression problem. How can we take this long string and compress it into some object where we can still locally access what the string is? And then another interpretation is, as like a circuit synthesis problem. Your Intel, you want to compute some function. What is the best circuit you can have for computing that function? So that's just a couple different ways to think about MCSP as a complexity problem, as a compression problem, and like a circuit building problem. And this problem actually has like a really long history, really interesting history. So in the 1950s, mathematicians in the Soviet Union were interested in thinking about computational problems that you couldn't beat via brute force. Couldn't solve without brute force. And they were thinking about like what types of computational problems could you, not do much better than brute force on. And MCSP was to them one of the most natural candidates for this. And they kind of came up with this conjecture that you can't do any better than just brute forcing to try and figure out what the complexity of a string is. And kind of amazingly, in 1959, a mathematician named Jablonski said he had proved the parabolic conjecture. And what's kind of amazing about this is had Jablonski, actually proven the parabolic conjecture, he would have proved P not equal to NP before the problem was even formalized. So of course, it's not quite what he had proven. He proved it in like a very restricted model, but he showed that like in this restricted model, MCSP couldn't be solved faster than brute force search. And then about 10 years later, the parabolic conjecture was kind of proven again. Dektiar had given a proof. And of course, this also doesn't quite resolve the conjecture in truth, but kind of interestingly, what he did show is that there's an oracle relative to which P is not equal to NP. And what's kind of amazing about this is, again, like the idea of oracle computation and relativization hadn't been really formalized, and it took a couple years later, 1973, it was really formalized with Baker, Gill, and Salovey. But he implicitly had shown that there's an oracle relative to which MCSP cannot be solved faster than brute force search. And then again in 1973, when Levin published his famous version of the Cook-Levin theorem, which basically established the theory of NP completeness, he actually delayed publishing his proof because he wanted to capture MCSP within this framework. He really wanted to show that like this parabolic conjecture was kind of equivalent to this question of how fast can you solve SAT. And so you have like this really long history that begins in the Soviet Union, and then the problem kind of faded into the background a little bit until about 2000, when it was really revitalized by the work of Kabinets and Tsai. What they did was they realized that this problem MCSP is kind of naturally connected to cryptography, and it's naturally connected to then the new natural proofs barrier, which Razborov and Ruch had come up with, and they kind of revitalized studying this problem, and that begins what I guess is like the modern history of MCSP. Yeah. Okay, so I've told you a little bit about what MCSP is, and I've told you that like people have thought about it for a long time, but like why should you care about MCSP now? And I think for those of us who are interested in MCSP, kind of like the high level picture here is about this search for fundamental problems. And if you look back in complexity theory and think about like what problems have we learned the most from, what have we like gained the most understanding from, there are problems that kind of stand out like SAT. And what's interesting about SAT is like by studying it, we learned about all these amazing things. We learned about NP completeness. We learned about PCPs, built practically useful SAT solvers, developed a theory of fine-grained complexity. And I think what I would argue is that SAT seems to be a fundamental problem in that like natural questions about its complexity, like how hard is it to compute in the worst case? Can you approximate it? How hard is it in practice? Led to these like important, often unexpected advances in the field in computer science. And it raises a very natural question. Can we find more fundamental problems? Like what can we learn from them? And SAT's a pretty fundamental problem, and it would be nice to have a problem that's like even half as fundamental as SAT. And you might wonder if we can even find another one like that, which makes the following quote like really bold. MCSP is more fundamental than SAT. And what researcher would dare utter such a blasphemous claim? Well, Rahul's me. This isn't me, Rahul. This is actually Rahul Santhanam. And so you're probably wondering why all these Rahuls are so interested in MCSP. And it's probably it's primarily because of the connections the problem has. It has connections to cryptography. It has connections to learning. And like, these two things are very interesting because like, SAT, for all its wonderful connections, hasn't had such an influence, large influence in cryptography and learning. And then there are also connections to things that you like might expect, like structural complexity theory, average case complexity, and circuit complexity. And so it has all these wonderful connections. And we also, don't really know much about the problem, like really basic questions about the problem we don't know the answers to. Is it NP complete? This has been open since, Levin in 1973. Is it hard to approximate? We don't know. Can you beat the naive brute force algorithm? We don't know. What we do know is that like each one of these three questions relates to structural complexity theory, average case complexity theory, and circuit complexity. And how exactly do they relate? Well, we have these theorems which say if some specific thing is true about MCSP, then we get a solution to a long-standing open problem. Okay, so what do I mean by that? Well, suppose MCSP is NP complete. Now, Murray and Williams actually show that this implies a breakthrough complexity class separation. X is not equal to ZPP. If you can show that an approximation to this problem is NP complete, then by like a wonderful theorem of Hirahara, you get that computing NP on average is actually as hard as computing NP in the worst case. Now, it's not clear exactly what these terms mean. I'm going to talk about this a little bit again later, so we'll circle back there. And then another thing is if you can show for some version of MCSP that it doesn't have like basically linear size circuits, then there's this hardness magnification phenomena that McKay, Murray, and Williams showed occurs, where you actually get to lift this like barely superlinear lower bound on MCSP to a super polynomial lower bound against NP. So we have all these interesting connections where like basic aspects about the complexity of MCSP seem to relate to like significant open problems in other areas of theory. Yeah. Okay, so I've talked a little bit about like why you might care about MCSP, but now I just want to come back around and define the problem a little bit more formally. Okay, so the minimum circuit size problem is going to take two inputs. The first is the truth table of a Boolean function. So, just the list of values the function takes on all of its inputs, represented as a string. And note that this string here is going to be of length 2 to the n, because it's going to have n inputs, and it's the list of all the values the function takes. And it's also going to take some size threshold, which is going to represent what complexity you're asking about. And it's going to ask, does there exist a circuit with at most S gates that computes F? So the notion of circuit here kind of varies depending on your applications, but for us, you can just take it to be the usual notion of and or not gates with fan into. Yeah, is there any questions about how this problem is defined, or maybe any questions about anything I've discussed so far? Okay, great. Right. So you might ask, like, what makes this problem like so interesting and have all these kind of interesting connections? And it seems to be that it's like a meta computational problem. It's a computational problem about computing computational problems. And in some sense, it's this aspect of it seems to allow it to be connected to things like learning, to things like cryptography, in interesting ways. And it also makes the problem, I'd argue, aesthetically pleasing. And it means you can make kind of fun titles like The Complexity of Complexity. Which leads me to say, what is the complexity of this problem? We don't know too much about it. We do know the problem lies in NP for kind of the easy reason. If there's a circuit of size at most S computing this function, I can give it to you as a witness, and you can actually check that this circuit computes the function. Yeah, now this might seem like an inefficient operation because you have to evaluate the circuit on all of its inputs to see what function it computes. But note that in your input, you're given a string of length 2 to the n here. So you can actually efficiently evaluate, or in polynomial time, evaluate this circuit to see if it computes this function. So it is an NP. So, okay, so the problem's an NP, natural question. Could it be in P? Well, actually, we don't think the problem is in P. And the reason is, if it were in P, then cryptography as we know it wouldn't exist. And I'm going to talk a lot about this a little bit later, but it basically means that we don't expect the problem to be in P. Okay, so we have some problem. It's in NP. It's almost certainly not in P. The natural question is it NP complete? Well, as I mentioned earlier, this is a big open question. If you ask me, of course it's NP complete. It has to be. But there's definitely other researchers in the field, other prominent researchers in the field who believe that like maybe it's NP intermediate. That is, it like lies outside of P, but isn't quite NP complete. And kind of like resolving this question is a very interesting question. All right, so that's kind of like the vanilla version of MCSP, but there are other versions that crop up in these connections. So the regular version of MCSP is this: you get as input a function f and an integer s, and depending on the size of the smallest circuit computing f, you either say yes if it's less than or equal to s, or you say no if it's greater than s. So that's like the normal version. But you can also talk about like approximation versions, where you still say yes if the complexity is less than or equal to s, but now you only have to say no when the complexity is a factor of k greater than s. And if it's in between this area, you can say either yes or no. There are also these interesting average case versions of MCSP, where now you need to compute MCSP, but you're allowed to make errors, or in some sense. So computing MCSP with 0 error means that, if the complexity is less than or equal to s, you can say yes, or you can say I don't know. And the point is, like, whenever you say yes, you have to be correct. And similarly, whenever you say no, you have to be correct, but you're allowed to say, I don't know, a certain percentage of the time. And so that's like the 0 error average case version of MCSP. And there's also a one-sided error version of MCSP. And in this version, you're allowed to make errors on one side. You're allowed to say yes when in fact the answer is no. But the point is, whenever you say no, you must be correct. And this, the reason why I mentioned this MCSP with one-sided error is actually, it relates pretty importantly to the theory of natural proofs and the natural proofs barrier. If you don't know what this means, it doesn't matter, but if you've heard the term natural property against size S, this is exactly what MCSP is with one-sided error. And this is kind of like one of the interesting connections the problem has. All right. So I want to circle back to some of these connections. Like, what are they? I said that there are these connections to cryptography and learning and that I think are particularly interesting. So, like, what are they? Right. So kind of a central object in cryptography is the existence are one-way functions. And if you have one-way functions, you can get all these great things. You can get PRGs, you can get private key cryptography, you can get commitment schemes. These objects are really central to cryptography, but from a complexity theoretic viewpoint, our understanding of them is not really that great. The question of whether one-way functions exist doesn't really relate to like the central objects in complexity theory, like P and NP and stuff like that. And kind of interestingly, MCSP seems to have some sort of relationship with this. And the hope is that maybe you could capture the existence of one-way functions using MCSP. And so what do I mean by this? Well, already about 20 years ago, people observed that if one-way functions exist, then MCSP can't be in P. And kind of the reason for this is as follows. The existence of one-way functions kind of, implies that things like PRGs, pseudorandom generators exist. And like if you squint at a pseudorandom generator, what is it doing? It's like saying it's presenting, it takes as input some small seed, and it's like spitting out something that's like a really large randomish string. So it's kind of outputting the string that is like really random and chaotic looking, but is actually truly ordered. And MCSP can tell the difference between order and chaos, so you can't kind of fool MCSP with PRGs. And so that's kind of the intuition for why MCSP could be used to break one-way functions. And so the way I kind of like to informally think about this is MCSP is hard for cryptography. It kind of represents a universal attack. And of course, MCSP being hard for cryptography, I mean, that's kind of interesting, but also SAT's also hard for cryptography. Like if SAT could be solved easily, you could break all of crypto. Why is that so interesting? Well, the hope is that maybe MCSP is kind of complete for cryptography. Maybe you could actually pull a one-way function out of the hardness of MCSP. And this has been something that people have been studying for or people have been thinking about for a couple of years, and there's been some interesting progress that actually showed, so Santhanam earlier this year published this result that showed conditioned on some hypothesis, the existence of one-way functions is actually equivalent to zero error average case hardness of MCSP. MCSP with these brackets basically just means that the size parameter has been fixed to a specific value, but for the purposes of the slide, it's not so important. So conditionally, you get this kind of equivalence between the hardness of MCSP and one-way functions. And then kind of excitingly, just a month ago, Liu and Pass showed that a variant of MCSP, basically the variant switches the model of circuits for Turing machines, they show unconditionally that there's an equivalence between the average case hardness of this problem and the existence of one-way functions. So I think a very exciting avenue of research here is to really flesh out what this connection is. Right now we kind of get the feeling that the average case complexity of MCSP is really closely related to one-way functions. But a good open question is whether the worst case complexity of MCSP should also relate there, because we know in certain settings, as I'll describe later, that the average case complexity and the worst case complexity are the same. So it raises the exciting prospect that you could actually base the existence of one-way functions on the worst case complexity of some problem. And so I think that's really exciting. Another area that MCSP has a surprising relationship to is learning. Kind of a foundational question in learning theory is when can you learn functions? And, can one learn functions when they have small circuits? And so what exactly do I mean by learn? I don't want to get into the precise model. Precise model is here, but roughly, there's some concept that you get to ask questions about, and you want to get the gist of it. You want to mostly figure out what that concept is. And what you'd like to do is anything that's easily computable, you'd like to learn it. And you can ask for what circuit classes can you learn things that are easy to compute. And the reason why you would want to consider circuit classes is that kind of early on, people realized that if cryptography, for cryptographic reasons, you can't expect to learn anything with small circuits. But they did realize you could learn kind of simple things with small circuits, like so p-poly here represents general circuits, and so people realized you could learn DNFs and constant depth circuits. But for about 25 years, it wasn't clear for other classes, like constant depth circuits with some stuff added onto them, whether or not you could learn them. And it was resolved using a connection to MCSP. What people realized, or what Carmesino and Pagliazzo, Cabinets, and Kolokolova realized, was that you can actually learn functions with small C circuits if you have algorithms for CMCSP. So CMCSP here is just the minimum circuit size problem for a restricted class of circuits. So what's the smallest DNF for computing a truth table, or what's the smallest constant depth circuit for computing a truth table? And they realized that even if you had an algorithm for MCSP with one-sided error, you would get these learning algorithms for small circuits. And they used that to show that you could learn this class of circuits that wasn't clear if you were able to learn efficiently. And there's been some follow-up work on this about different models of learning and what you can do. I'm not an expert on that kind of stuff, but it seems like there's still interesting questions here about the the relationship between learning and MCSP. And even if you combine this with the connections with cryptography, an interesting question is, could the complexity of MCSP, the complexity of learning, and the existence of one-way functions all be connected in some way? These are the questions that people are kind of investigating. And finally, I want to talk about average case complexity. I already mentioned this result a little bit earlier, and it's motivated by this question: how hard is it to compute NP on average? So kind of common criticism of complexity theory is that it's focused on worst case complexity. How hard is it to solve SAT on worst case instances? But in practice, you don't really see worst case instances. You're seeing instances from some distribution. And you can wonder, how hard is it to compute NP if I only need to answer most of the queries or stuff like that? And this question, for a long time, it was difficult to relate this question to our standard complexity theoretic questions like P versus NP in the worst case. And kind of this really cool result by Hirahara said, well, actually the worst case complexity of NP, solving SAT in the worst case, actually reduces to computing NP on average with zero error if the approximation version of MCSP is NP hard. And I'll review the definition of this in the slide, but just for now, you can think of it as the multiplicative approximation of MCSP. And so what he does is he actually shows that the worst case version of approximating MCSP actually reduces to computing MCSP in the average case with zero error. And this was a really exciting result because there were these kind of no-go theorems that said you can't do this using the usual techniques. You can't do this using black box techniques. And MCSP, being kind of this meta-computational problem that involves circuits in its definition, kind of allowed Hirahara to open the black box and give this worst case to average case reduction that's not black box, and is very interesting. Of course, okay, and to be clear here, we don't know whether or not this hypothesis is true, but it gives this conditional result between worst case and average case complexity. And now, before I move on, I just want to take a step back here because I've mentioned these relationships to cryptography. I've mentioned these connections to learning and the average case complexity of NP. And kind of the feeling I get, and I think the feeling that people in this field get, is that maybe there's something going on here, because in the same way that SAT kind of unified the picture of worst case complexity, by connecting the difficulty of all these natural problems, maybe MCSP plays a similar role in average case complexity. Maybe it's like this lodestar by which you can connect all these different questions in average case complexity. And maybe it is, maybe it isn't. I don't know. My hope is that it is, and I don't know. I get that's the feeling I get from these results. I mean, one-way functions, learning on average. These are all fundamentally average case notions that we weren't really able to connect to SAT, but we can connect to MCSP. All right. So there are also more connections to structural complexity and circuit complexity that are really interesting, but I decided to focus on the others with the time given. All right, and now I want to return to the title, because the title of this talk is about order versus chaos. And, there is this result that I just mentioned at the last slide by Hirahara that said, like, this gap version of if this gap version of MCSP is NP hard, we get this wonderful consequence. And we actually get other wonderful things too, like complexity class separations and stuff like that I didn't mention. But you can ask, how likely is this hypothesis to be true? And if you ask me, I don't know. And, I've asked other people, I've asked Hirahara, I've asked Santhanam, and I think, people aren't sure if this problem should be NP hard. Certainly it's intractable. You could break all of crypto using this problem. But is it hard? I'm not sure. And that's what kind of spawned the title of this talk. So just to review what this problem is, you get this function f, you get this integer s, and now you can look at the complexity of the small circuit computing f, and you have to decide whether or not it's less than s or whether it's greater than s times this factor. And this factor here is really large, n to the 1 minus epsilon. And n is going to be the length of the input. So basically, every function is going to have a circuit of size capital N. So like the approximation factor here is really huge. It's asking, like, do you have like a really relatively ordered circuit? Like, do you have a small circuit, or do you require basically maximum size circuits? And to me, this question is it NP hard to distinguish order from chaos? Is it NP hard to distinguish between things which have computational order that can be described by small circuits, or really cannot be? To me, this is a very interesting question, and both like philosophically and practically in terms of the consequence it has. And it really drew me to the field. So like, before we can answer this question, which I think people aren't sure how to answer, we still have to resolve this like open problem since the 70s. Is MCSP NP hard? And, if you ask me, the answer is of course yes, but we really don't know how to prove it. In fact, there are these like no-go theorems which say, we can't prove it using this technique and stuff like that. So Ryan Williams has this quote that I fished out of one of his Simon's talks. If it is NP complete, it would have to require techniques that are not like any polynomial time reduction that we have ever seen. And the reason Ryan is saying this is, like, if you think through, what would it mean to give a reduction, right? So the difficult no instances of MCSP, the ones that like you can't determine are yes or no easily using brute force, what they correspond to are like these truth tables that require large circuits. And so if you had a reduction from SAT to MCSP, it's kind of like translating difficult no instances of SAT to difficult no instances of MCSP. So this reduction is kind of like implicitly providing functions requiring large circuits, which is like something we don't know how to do. We don't know how to produce functions that require large circuits. And what that means is, kind of, if you wanted to come up with a deterministic polynomial time reduction, you'd need a breakthrough. You'd need some sort of breakthrough that lets us understand the complexity of functions better and produce hard functions. And this is formalized by a couple different results. And so what that means is, like, is there really any hope of resolving this right now? Is there really any hope of showing MCSP as NP hard? Well, what this intuition or what this relationship shows is that if you're hoping for a deterministic polynomial time reduction, you need a breakthrough. But at least for me, this provides two different ways to slip away. I personally strongly believe that it should be possible to show that the exponential time hypothesis implies MCSP is not NP. And the reason for this is now if you allow yourself like much larger time reductions in polytime, all of a sudden now you don't need to provide functions requiring large circuits, but you can actually theoretically get by with functions that require only circuits of size 2n or 3n or stuff like that. And for me, it seems quite plausible that you should be able to prove ETH implies MCSP is not NP. And another thing is randomized reductions, right? So like deterministically, we don't know how to produce functions which require large circuits. But if you use randomness, then like a random function is going to require large circuits. Random functions, it's not going to have any order at all. So it's not clear whether there should be a barrier to proving MCSP is NP hard using randomized reductions. And so it would be really interesting to either prove it's NP hard using randomized reductions, or show that there's some barrier there, and no one really understands whether there should be or shouldn't be. Right, and so this finally brings us to our results. So I think this is a natural place to pause in case anybody has any questions about what I've said so far. Okay, so now let's talk about our results. And so the main result, what I'm going to talk about here, is that MCSP for multi-output functions is NP complete under randomized reductions. Yeah, so let me just talk about what MCSP for multi-output functions is. So now our input is going to be a truth table again, but now it's the truth table of a multi-output function, a function that takes n bits to say m bits, and still a size parameter s. And now you're going to say, does there exist a circuit computing f of size at most s? And so what exactly do I mean by a circuit computing a multi-output function? I'm going to say a circuit computes a multi-output function if each one of the single bit output functions, that is like the function f sub I that computes the ith output of f of x, is computed by some gate in a circuit. So like, maybe this gate computes the third output, this gate computes the fifth output, and so on. So we're going to require for each one of the outputs bits, there's some gate in here that's computing that function. Okay. So the starting point of our reduction was a hardness result that was proved easy earlier this year. So there was this result that said that this other version of MCSP that I'll call helper MCSP is NP complete under randomized reductions. And what exactly is helper MCSP? I'll describe it for you. So now instead of computing f with a regular circuit, I'm going to describe a model where you can compute f with helper bits. So usually when you're trying to compute this function f, you need to design this circuit that takes an input as x and computes f of x. But now imagine you were given this advice function that gives you advice on every input. And so I'll call this advice function alpha. And so it's going to give you k bits of advice on every input. And now you can ask now you can design circuits that not only take x as input, but also takes this advice here as input. And now you want to compute f given x and the advice. And note that the advice does depend on the input x. So now you can ask, now you can define this quantity, which is kind of like the conditional circuit complexity or the relative circuit complexity. So the circuit complexity of f given alpha is going to be the size of the smallest circuit that computes f using alpha as help. And what this result showed is that computing this conditional circuit complexity quantity is NP hard under randomized reductions. All right. So our approach was, can we calculate this conditional circuit complexity quantity using multi-output MCSP? If we could, then since this quantity is NP hard to compute, then obviously multi-output MCSP is NP hard. So what was our approach? So here's the first attempt. Kind of there's this suggestion. Our first attempt was to kind of hope for a chain rule, and this is kind of inspired by the fact that there's like a conditional complexity quantity there.
Rahul, sorry,
Yeah.
there's a question from Shahar Lovett. In
Yeah.
the helper MCSP problem, is alpha part of the input?
Oh, yes, sorry. Yeah, alpha is part of the input. So your input is going to be the truth table of a Boolean function f and the truth table of an advice function alpha. I'm sorry, yeah, I should have made that clear. Hopefully, yeah. Okay, so now we want to compute this quantity using multi-output MCSP. And so our first attempt was to hope for a sort of chain rule. So we have this function f that we want to compute its complexity relative to alpha. Maybe you'd hope for computing f and alpha, like the multi-output function that requires you to output f and alpha, happens to equal the complexity of f relative to a plus the complexity of alpha. Now, this is a little bit too much to hope for, but if you had it, then we would be done, because you can say the complexity of f relative, you can compute the complexity of f relative to alpha using MCSP by, subtracting off the quantities. Both these quantities are multi-output functions. You can compute the complexity of them, and then you'd be done. So you could calculate the relative complexity if you had such a chain rule. But is such a chain rule true? Well, one direction is true. Certainly, if you want to compute f and alpha, you could first compute alpha and then compute f given alpha. So one direction is true, but the other direction is false. And kind of the reason is, like, maybe in computing alpha, you actually computed some stuff that's really helpful for computing f. And kind of a simple example of this is if f is the OR of 2 bits and alpha is the OR of 3 bits, then you could compute them both together using 2 gates. First compute this OR and then OR it with a 3rd bit. So the complexity of computing both of them is 2. But the complexity of computing just alpha is also 2. So you get that this quantity here that we're trying to use to estimate the relative complexity is just 0. So this chain rule is false. So what we tried to do is we tried to fix this chain rule. And how are we able to do that? We tried to add more outputs. In particular, the problem with the chain rule was that in the way that you compute alpha might help you compute f. So what if we could force you to compute alpha in a certain way that wouldn't help you to compute f? And that intuition, seems very difficult, because in complexity theory, it's really hard to argue that an optimal circuit does something specific. And we kind of get around this in a way that's almost like cheating. So how do we force it to compute alpha in a specific way? Well, we're gonna force it to compute each one of alpha's components in a specific way. So alpha 1 up to alpha k are like the single output versions of alpha. This alpha 1 computes its first bit, alpha k computes its kth bit. And we're going to force it to compute alpha 1 up to alpha k in a specific way. And the way we're going to do this is like with a really elementary lemma, which I like to describe as some self-help advice. You are the best at being you. And it's like this. Suppose we had some very specific circuit for computing, say, alpha 1. And I'm making no assumptions about this circuit, really. I mean, it could be extremely inefficient. It could compute a bunch of irrelevant things before it gets to computing alpha 1, but it's just some circuit that computes alpha 1. So there's like a really natural multi-output function associated with this circuit, which I call like the computational history of this circuit, which is just for each gate in the circuit, I'm going to have an output bit corresponding to that, and on input X, it's just going to output what that gate output. So like on input 0 to the n, the first bit of this is going to be like what the first gate output. The second bit's going to be what the second gate output, and so on. So this is just, this function is just describing exactly what the circuit is computing on X. And, kind of trivially, or by construction, C is a circuit that is computing its own computational history. Each one of these outputs is computed by a gate, essentially by construction. So we know that the complexity of computing this computational history function is at most S. On the other hand, it kind of can't be any less than S, because like there's S outputs, and as long as those S outputs are distinct, that is that like, as long as there's like no redundant gates in the circuit, you're going to need at least S gates to compute S different functions. So the complexity of computational history is exactly S. In particular, C is an optimal circuit for computing computational history of C. Like every circuit is, almost every circuit is optimal for computing its own computational history. In particular, it's like basically the only way to compute its own computational history. And the way that we use this is as follows. We're going to use this to force, in the chain rule, the circuit to compute alpha in a specific way. In particular, our goal is to calculate the relative complexity using multi-output MCSP, and we want to do this using a chain rule. So we just fix some very specific way for computing each of the bits of alpha. So let's just say the naive DNF, like some specific way. It's not so important what that specific way is. And now we hope for this new chain rule, which says that the relative complexity of F given alpha is the complexity of computing F along with alpha, along with all the computational history in some specific way for computing each of the bits of alpha, minus the same quantity without F. So how hard is it to compute, what's the difference between computing all of these things with F and without F? And our hope is that that's roughly approximating the relative complexity. And this is still false, basically for the same reason as before, that like in computing these things, you could still maybe have something that helps to compute F. But it's false in general, but it's true for the specific F and alpha used to show hardness for computing the relative complexity. In particular, the hardness for computing this relative complexity uses a random F and a nearly random alpha. And because these things are kind of randomized, maybe there's some things that are like potentially useful when you compute these things, but are they going to be that useful for like a random function? We're able to exploit that randomness to say, that in fact these two quantities are roughly equal. And then, now we have this way of approximating the relative complexity using multi-output complexity, and that gives us NP hardness for multi-output MCSP. And in truth, when you open the box here, what's happening is we're actually reducing set cover to multi-output MCSP. All right. So yeah, thanks for listening. I'm happy to answer any questions anyone has.
Is it okay if I just chime in with the voice?
Yeah, sure.
Okay. Thanks so much for your talk. One thing I'm wondering is does this chain rule have any relation to things from circuit complexity, such as the Karchmer-Raz-Wickerson conjecture? So this is composition is different in their case. They have this relation where they actually copy one of the functions G as n many inputs to F, but there's this similar one way down that's pretty easy to show, but the other direction is really unclear. So any familiar?
Yeah, so I'm not so familiar with the KRW stuff, but so my guess here is that probably beyond that relationship where like one direction is easy to prove and the other seems difficult, I'm not sure, it's not clear to me that one could connect these two ideas, but I have to think about it. Yeah, I guess. So one takeaway you might say is like, so I think that this chain rule here is like is a much easier question than the KRW conjecture, but even in this kind of like easier setting, we still need to make use of this randomness in order to analyze things. So maybe one really high level takeaway you could say is maybe is there any way you could is it easier to prove KRW using randomized functions in some way prove KRW on average or something like that? I guess that would be my takeaway. Does that answer your question?
I got you. Yeah. Thank you.
Yeah, thank you.
So there are two questions in the chat. So first, Varun is asking, how is this problem connected to Kolmogorov complexity?
Mm-hmm.
And Shahar Lovett's asking whether you can say something about how the randomized reductions are used to prove that helper MCSP is NP-hard.
Yeah, okay. First I'll answer the question about, so the question was, how does these problems relate to Kolmogorov complexity?
Yes.
Yeah, so that's a great question. You can think about MCSP as like kind of relating to like a time-bounded Kolmogorov complexity. And so there's various ways that people talk about time-bounded Kolmogorov complexity. I think Eric Allender has like an excellent survey where he talks about all these like different variants of ways to make Kolmogorov complexity effective. I mean, so Kolmogorov complexity is a great theory, but like the one downside to Kolmogorov complexity is like you can't compute Kolmogorov complexity. So like there are all these different notions which make Kolmogorov complexity like kind of computable. I mean, still like things like MCSP we expect to be NP-hard, yeah, so I would say the relationship between these measures and Kolmogorov complexity is like attempting to make like a more effective theory of complexity of strings, and that also takes into account how the time you need to compute the string. Another relationship here is that, at least in this work, we kind of our intuition was based around this like chain rule, which was something that you actually have in Kolmogorov complexity. I would say the relationship in this work actually ended up being pretty strong in that like we were kind of inspired by this Kolmogorov complexity thing. But yeah, so the problems are related, and even there's some technique relationship. I think there is some conjecture that somebody has about maybe. Okay, yeah, I'll skip that. Yeah, hopefully that answers your question. And then Shahar's question was, can I say something about how the randomized reduction for helper MCSP works? And yeah, I can say something about that. I made a bonus slide. Let's see, how do I access this bonus slide? Oh, okay. I thought I made a bonus slide. I think maybe it's in another copy of my PowerPoint. So, okay, I'll just describe it. Can I describe it? Maybe I can find my other PowerPoint. Yeah, sorry about this.
Okay, so perhaps what I'll do is I'll take us offline now. We can like continue with questions or chatting. Mm-hmm. And one thing I wanted to say was that, so just to advertise the upcoming talks. So on June 3rd, we'll have Michael Kim from Stanford, who's going to talk about learning from outcomes. And then June 10th, Cliff Stein from Columbia will talk about parallel shortest paths. So again, thanks so much for joining, and we'll continue. I'll just go offline now and stop recording, but we can continue chatting.
All right, great. So are you able to see